Sorry. Okay. So thank you very much. I'll recognize I'm between all of you and the lunch, so I'll try to stick to the time. The presentation is about seismic attributes for enhanced faults and fracture detection, and we'll share some of what we think are fast pay approaches to our teams. The work was done by our R&T team in Austin, Texas, and also the exploration team in Norway, Alexandra Cournot, and we mostly use software from DGVR Sciences, and we have a collaboration with them. So Nanne Hemstra is also participant of this work. As in the other presentation I made today, we are trying to characterize these two types of unconventional reservoirs that we identify in several basins. The ones that are self-source, like the Eagle Ford or Vaca Muerta, versus the ones that are non-self-source, like the Middle Bakken, for example, or the Austin Chalk. Some of these involve geochemistry, organic geochemistry analysis to fingerprint the oil source and the allocation, and differentiating how much of it is self-source versus not self-source. The case here, we'll go through mostly the Eagle Ford data set. And for that, I'll highlight some of the part of the workflow, the geomechanical mapping and critical stresses that we do with FRAC and ICON modules. We also highlight the extract rock and fluid properties that we're doing with the chimney cube from OpenDetect, and some of the folding fractures automatic attributes. There is also a map of fluid pathways and fingerprinting source rocks using diamondoids and chimney cube. In this presentation, I'll focus on the chimney cube results and not get much into the diamondoids and the organic geochemistry that we're using to fingerprint the oil sources. With that, a first view of the mechanical stratigraphy and the structural controls that we see on producibility. Here you're seeing a seismic view from a 3D volume that we have available for the Eagle Ford in West Texas. And in the pie charts, you see the proportion of oil that we're producing from selected wells in that acreage. And you notice that towards the shelf margin, which is to the south, there is much gas production mostly, not much liquids. As you move to the north, the amount of liquids increase. And here we run several attributes to detect fluid-escape features and also faults and fractures. You are seeing one, let me just use the laser pointer here. One, the chimney cube attribute from OpenDetect. All the green areas are identifying fluid-escape features from deep on the basement and the salt layers, using the major faults that connect the hydrocarbons from deeper sources all the way to the Eagle Ford reservoir and others. The geomechanical analysis that we have done, we take FMI logs and run a complete geomechanical workflow and identify areas like you can see here in blue that are of higher fracture clustering. In this case, like in the Buda Formation and the Middle Eagle Ford, and then up on the Upson. So these fluid cave features we see are connected to deeper rock intervals, and they are tying to areas of increased production. These major listric faults are make conduit for fluid migration. So we wanted to map this in more detail, and that's part of what we're going to show. Then in the next slides, this is a plain view of the area, and I'm highlighting in red the two wells that are the high producers in the area, and this was about the cross line that I showed before in the 3D. Here's where we have these major listric faults, where we also see on this first attribute called TFL, fault likelihood, the amount of fractures and faults increase when you are around these major listric faults. Then there is a zone of not much activity fracture-wise, even though you have big faults through the area. And then towards the shelf margin to the south, there is an increase in fracture density. Some of the attributes we tried well was the seismic anisotropy. And this one specifically is highlighting in those areas a higher anisotropy than we see on the rest of the volume by these really white colors and some of the oranges. The chimney cube analysis highlight fluid cave features on here, and I have a boost image of that in the next slides. Here you can see some of the wells and laterals, the best producers that I show in the previous slides, and even though they're landing on the Eagle Ford, they are in this case 3.4 miles down deep of these halokinetic faults. And what you see there is the TFL attribute in black, highlighting these faults and fractures. And then you see in green the fluid cave features from the chimney cube attribute. So here we then see a connection of these fluid cave features and through falling fractures from Jurassic intervals to the Cretaceous reservoirs. We did that study consistently on all other wells in the area. Another high producer is 1.37 miles down deep from this anomaly, where we have, again, falling fractures deep to the basin, to the Jurassic interval, and fluid cave features indicating migration to the well. And this last example is well right on top of one of these features, where the listric fault is pretty well imaged, and the fluid cave features are also pretty well established from this neural network approach. The other thing that we did was to try different attributes to see which one give us the best correlation with what we were seeing on the course. And here you see for a smaller seismic volume, the result from the TFL fracture density attribute for the Olmos, which is on the shallower section, and the Eagle Ford, which is on the base, Austin Chalk. There is a azimuthal anisotropy travel time-based approach that was also tried by some of the geoscientists in our team at the time, and fracture FracTex plugin from DGV as well, which shows the best correlation with the TFL. Look at these folds that are really well imaged in both of them. and we used here the similarity attribute from FracText. Um, this can also be applied to volumes, and we can establish the main direction of the faults in the area, and extract the fault planes as we please. Let's say we're interested mostly on these major east-west faults. We can just select those and extract them for further analysis. Um, the other application that we have is the fracture density volume. So once we calculate the TFL attribute, we can extract the amount of fractures from the seismic data using this workflow. And in this case, it's a small volume in West Texas, and we have all these yellow areas are predicted to be of higher fracture intensity versus the blue areas where we don't see much faults or fractures, and the green areas that are basically not lining up on the major faults. These faults can be also extracted, and we have done so for more specific reservoir modeling in other softwares like Petróleo, for example. The next part of the workflow was, as I mentioned, to correlate the areas that are critical stress. And for this part, and the whole correlation to the Moore cycle, to help us identify when we have open versus closed fractures and in the formation. So by this analysis, we in this specific well, we use the FMI to start with, and came to results on what's the set of fractures that are more prone to reactivate, like you see in this graph. Something we apply the same in Turkey. And for example, you see a seismic, the TFL attribute on the area there, and these extractions help us define areas for drilling the wells on areas with a higher fracture intensity, like so, versus other areas where the predicted amount of faults and fractures is the lowest. We did that, and this came out as a pretty good exercise to mine that gap between the well log data and the seismic data. And for that, we create this pseudo FMI. So what we did was we took the TFL attribute that you see here and establish an area of interest around the wellbore to be drilled. And then Petrel, we used an orbital projection of that seismic attribute, in this case the TFL, as I mentioned. And then we compare that with the actual deep hole data for the well we were drilling. But this really allows us to predict areas with major fractures and washout zones, and areas where the hole will not be that stable during drilling. And here you see some examples. We define from the pseudo FMI areas where we can attempt coring, and because there was not many faults and fractures detected, and they were a pretty good match for where the core was collected. But there are also areas where we got a major fault indication during drilling, and those came out straight out of the pseudo FMI. And after comparing the well results with the prediction, we predicted all of those events ahead of the drill bit. And then the prediction with the faults and fractures, it's also important. And in that case, we have what is it? A good 2 out of 3 um, um, correlation between the pseudo FMI and the faults and fractures.
Jesús, one second, please. A los participantes, si tienen preguntas para los presentadores, las pueden hacer en español o en inglés como deseen y serán traducidas en ese caso al final. Sorry, Jesús, we have 3 more minutes.
Great. These are the conclusions. So in here, I just listed 2 of the parameter sets that we use for this work. For the TFL, well, it's important to run an edge preserving smoothing filter first and decide your extraction strategy. You want to use these faults for volume for reservoir models, or you want to extract the fault planes only. Start with a full strike 0 to 360 detection, and that would run smoother than limiting yourself to a specific angle stack. And for the seismic anisotropy, well, this is what gave us the best results, using Cray levels of 256 for fractures and 60 Cray levels for faults. And you can change the type of transformations on each of the areas, and also the best results were encountered with what you see listed here. There is this pseudo FMI is, I think, we think a proven solution to close that resolution gap between the seismic and the well log data. And we, of course, are doing more of these examples in other basins. And finally, a bit of promotion to the workflow. The workflow that you saw today, plus the organic geochemistry that it didn't cover, it's going to be published in the Journal of Petroleum Science and Engineering pretty soon. So with that, I'd like to thank you for your attention, and also Equinor for the publication of this work, and the exploration and R&D teams that collaborated to this. Special to DGBR Sciences for the OpenDetect software, and the collaboration we had with them for the fault and fracture detection. The seismic data was a courtesy from Sitel Services, Seismic, and the Icon Science was the software used for the geomechanics and interpretation module. So thank you, guys, and I'm open to any questions that you may have.
Thank you very much, Jesus. Maria is going to take some questions from the public.
Thank you, Jesus. Very clarifying and interesting. One of the attendees wants to make a question. Even district faults could be potential vertical migration pathways for this oil system. Seismic view shows no growth strata in target zones, so increase of natural fractures density could be related to post-sedimentary fault activity? I don't know if that's clear for you.
So I think the slides I show, there were 2 attributes, the TFL and the chimney cube. And those are for detecting both the faults and fractures and also the fluidiscape features. There are areas like I show in this presentation where we see a match between the faults and fracture acting as conduits for fluid migration and the fluid migration detection for the area. So yes, there are other cases where they don't match. You may have a fault and fracture detection, but there is no fluids detected. So in those areas, we didn't see charge from deeper sources. The ones I show, I think is compelling, the evidence for a migration from a deeper source using these major Listric fault systems. But I understand the concern of the person making the question. And for that, I think we use organic geochemistry to fully support the allocation and fingerprinting the oil that we were seeing detected in the seismic attribute.
Thank you very much, Jesus.
Jesus, there is one other question from Ramiro Lopez.
Yeah. Ramiro Lopez. So I should see the.
I'm sorry. He was
said
willing to make it orally. I'm sorry.
Yeah. Okay. Please do.
I'm afraid he's not in now.
Okay.
I offered him to write it, but.
Sorry, Jesus, there are no other questions for the moment. So thank you very much for your presentation. It was an honor for us to have you here sharing with us this special edition of this Congress.